Hi everyone, welcome back. We're going to continue our conversation with optimization. We're going to go ahead and practice a couple problems that are similar to ones that you had last time, but a little bit different, and also expose you to a couple different ones altogether. Okay, so this first problem says a closed rectangular container with a square base is to have a volume of 300 cubic inches. The material for the top and the bottom of the container will cost $2 per square inch. The material for the sides will cost $6 per square inch. Find the dimensions of the container with the least cost. Okay, so there's two different things going on, but before we get to trying to write our primary and our secondary equations, we want to take a look and we want to draw our picture. So go ahead and get yourself a rectangular container with a square base drawn. To indicate that we have a square base, we're going to go ahead and label both of the two of the sides as X for the bottom. And then we know we're told that it's a rectangular container, it's not a cube, so we're going to go ahead and give our height a value of y. All right, now we need to identify our two equations, our primary equation and our secondary equation. Okay, so our primary equation, remember, is the one that we need to maximize or minimize. So in this case, when you read through this, what is it that they are trying to minimize? If I read this correctly, they are asking for the least cost. So cost is our function that we are trying to minimize. So I'm going to say C equals. All right, now I need to figure out how to write an equation for this the cost of this box. Well, it says the material for the top and the bottom will cost $2 per square inch. And the materials for the sides will cost $6 per square inch. I notice the words there, square inch. Square inch tells me, of course, that I'm talking about area. So if I figure out, all right, I have a top and a bottom, okay, and it says that they will cost $2 per square inch. Well, the area for the top and the bottom is x squared. So I say I have x squared, but I just said I have a top and a bottom, but are both the same, so 2x squared. Then times, though, the cost for those is $2, so times $2. Okay, so that's going to be the top cost for the top and the bottom. Plus, the material for the sides will cost $6 per square inch. Okay, so obviously there's six total faces on a rectangular prism. We just talked about two of them. All of the rest of them will have a length of x and a height of y. And so we're talking about 4 rectangles, all of area x times y. And again, that is the total area for those 4 sides times $6 per square inch. Okay, so there is my cost function, and I'm just going to take one more step to clean it up, and it would be 4x squared plus 24xy. Okay, so there's my primary equation. Now I'm going to go ahead and look for my secondary equation. All right, so the secondary equation is the constrained amount that they give me. So if they look here, the volume is 300 cubic inches. That is my constrained amount. So volume, 300, is equal to, it's the volume of a box, length times width times height. Well, I know length and width are both x, so x squared times y. All right, so now, of course, we need to take our secondary equation and solve for either x or y. In this case, it's clearly easier to solve for y. So I would just say y is equal to 300 divided by x squared. All right, now I need to take that and plug it into my primary equation. Okay, so I'm going to go ahead and take my cost equation, and when I get to the y, I'm going to replace it with 300 over x squared. Okay, so I'm going to clean that up. So c equals 4x squared, then plus, all right, so here I can clearly see that this x is going to cancel into the x squared and just leave an x on the bottom. So 24 times 300, well, 24 times 3 is 72, so 7,200, and then I'm going to write this as x to the negative 1. Okay, so now I'm ready. I have my cost equation all in terms of one variable. I'm ready to go ahead and take the derivative. So c prime is equal to 8x plus negative 7,200 x to the negative 2. All right, I'm going to go ahead and set that equal to 0. So 8x minus, I'm going to put this as 7,200 over x squared. All right, I'm going to go ahead and add that 7,200 over x squared to the other side and put the 8x over 1. So I would have 8x to the third equals 7,200. Divide by 8. X to the third is 900. So x would equal the cubed root of 900. Okay, so once I have that x value, I need to prove that it is in fact a minimum, that it will in fact produce a minimum, because remember we wanted to minimize the cost here. Okay, so I set up my sign chart and I have C prime and C. I'm going to put the cubed root of 900. All right, so if you're freaked out about the cubed root of 900, well, I know a perfect cube that is definitely larger than 900 would be 1,000. And the cubed root of 1,000 is 10. So I know that 10 is definitely going to be a number that's bigger. And then a number that's smaller, you can pick anything. I'm going to just pick 2. All right, so if I go ahead and put those values in, and again, I'm putting them in over here to my C prime function. Probably this one's the better one. Okay, so 8 times 2, so 16 minus 7,200 divided by 2 squared would be 4. Well, 7,200 divided by 4 is clearly larger than 8x, so that's going to be negative, which means it's going to be decreasing there. All right, and then if I put in the 10, well, I have 8 times 10 is 80, minus 7,200 divided by 10 squared would be divided by 100. 7,200 divided by 100 is 72. 80 minus 72 is definitely positive. So increasing there. So this proves that, in fact, the cubed root of 900 would produce a minimum for the cost. All right, so that's my x value. If I remember correctly, it asked for the dimensions of the box. And so I have my x value. I now need to go back and find my y value. And remember, y is just 300 divided by x squared. So that's divided by the cubed root of 900 squared. And we're just going to leave our answer like that. There is my 2 values. All right, the second problem here says a Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the radius of the semicircle on a Norman window if maximum area if the total perimeter is 16 feet. Okay, so I have this picture here, and it's clearly we have a semicircle on top of a rectangle. Okay, so if we think about what we need to identify in here, we definitely have this radius, which I'm going to go ahead and I'm just going to call it x. Okay, so if the radius is obviously half the distance from the semicircle, then the base of my rectangle down here is going to be 2 of those. So I'm going to go ahead and call that 2x. And then my height of my rectangle, I'm going to go ahead and call y. All right, now I could have used r and 2r instead of x and 2x if I wanted to. All right, so I have those labels. All right, now I need to identify again my primary and my secondary equation. Okay, so read this through. What is the quantity that we either want to minimize or maximize? So find the radius of a semicircle on a Norman window of maximum area if the total perimeter is 16 feet. So it sounds like we want to maximize area. So what is the area formula for this Norman window? All right, well, I have 2 things going on here. I have a rectangle, and I need to add the area of the rectangle to the area of the semicircle. So I would say the area of the rectangle is length times width, so 2xy, plus the area of the semicircle. Well, I know the area of a circle is pi r squared, and a semicircle is half of that, so half pi r squared. Okay, so there's my formula that I want to maximize. Now, my secondary equation comes from my constrained amount. Well, I'm given a constrained amount of a perimeter of 16 feet. So that is what is locked in. I only have 16 feet of material to work with, okay? So my perimeter is 16, and that equals. All right, so again, I'm adding all the way around. So I have the base of my rectangle is 2x plus 2y's for both of the heights, both of the sides, so 2y, plus the circumference of a circle is 2 pi r, and then again I only have half of that, so half times 2 pi x in this case instead of r. Oops, over here this should have been an x as well. Hopefully some of you caught that. Okay, so I'm going to go ahead and clean up my secondary equation. So 16 equals 2x plus 2y plus half of 2 is just pi x. Okay, so at this point I want to solve for the variable that's easier. Well, since there's only one y and there's two x terms, I'm going to isolate the y value. So I'm going to go ahead and subtract the x's away. So I'd have 16 minus 2x minus pi x is equal to 2y. And then I'm going to go ahead and divide everything by 2. So I would get 8 minus x minus pi over 2x equals y. Okay, so now of course I got to take that pretty ugly expression for y and put it in my primary equation. So I'd have a equals 2x times 8 minus x minus pi over 2x plus 1/2 pi x squared. All right, so let's clean this up. So I'd have a equals 16x minus 2x squared minus 2x times pi over 2x. Well, the 2's are going to cancel, so I would get just pi x squared. And then plus half pi x squared. Okay, so I should notice that I do have some like terms here with the minus pi x squared and the plus half pi x squared. So I'm going to take one more step to combine those. So 16x minus 2x squared. So this would be like minus 1 pi x squared, and then plus half a pi x squared would be minus half pi x squared. Okay, so that now is my formula for area. I need to go ahead and take the derivative of that in order to maximize that. Okay, so a prime equals 16 minus 4x, and then this would be minus half times 2 is just 1, so pi x. All right, I'm going to go ahead and set that equal to 0 and try to solve for x. Okay, so to do that, I'm going to go ahead and try to move my x terms, I know I have 2 of them, over to the other side to make them positive as well. So that way I like dealing with positive things better. So I have 4x plus pi x is equal to 16. Now I can factor that x out, so I have 4 plus x times 4 plus pi equals 16. And now to get x by itself, all I need to do is divide the 16 by the 4 plus pi. So that is what my x value is, 16 divided by 4 plus pi. All right, so of course, in order to finish and make sure that that is our answer, we need to verify using a sign chart that this will in fact maximize the area. So I know it's a weird number, but again, we can kind of think our way through this. All we're doing is having to choose numbers to the left and to the right of it. So this is our a prime and our a. All right, so if I think about pi is like a little bit bigger than 3, so 16 divided by 4 plus 7, well, 4 plus 3 would be like 7, so 16 divided by 7, I know it's going to go in a little bit more than twice. And so I would say that a number smaller would definitely be 1, and a number bigger would definitely be 3. Okay, so I should be able to go ahead and test those into this right here. So 16 minus 4 times 1 would be 4, so 16 minus 4 is 12, minus pi is still definitely a positive value, so showing that a is increasing there. All right, then a number bigger than the 16 divided by 4 plus 5, we said was 3, so 16 minus 4 times 3 is 12, would be 4, minus pi times 3 is like 9, so definitely going to be negative, so decreasing there, showing of course that this is a maximum. All right, and if you remember correctly, they only asked for the radius, and our radius was labeled with an x. So the only thing we needed to do was find our x value, which we did. We don't have to plug that back in and find any other dimensions. Okay, these next two questions are a little bit different. They ask us to determine all the points on the curve y equals x squared plus 1 that are closest to the point 0, 2. So I'm going to start by just sketching y equals x squared plus 1. Okay, it would cross the x-axis at 1 and would of course be an upward facing parabola. And they said what points on that curve are closest to the point 0, 2. So this would be like the point 0, 2. Okay, it's on the y-axis and it's 2 up. All right, so you can kind of see here, if I'm looking on this curve, you want to pick a point that's closest to that, or points. All right, well, you can see that probably a point somewhere in this region is going to have a closer distance than if I start to pick a point way up here, okay, or even straight down. All right, so which point is closest to that? So how do we do that? Well, if we're talking about finding a point on the curve, the first thing I want to do is just randomly put a point on the curve and call it x comma y. All right, now I want to take a look at minimizing this distance. Well, do I know a formula for distance? I certainly do. All right, so the distance between 2 points is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. You should remember that from geometry. Okay, so now that since that is our value, our quantity that we want to minimize, we would say that that is our primary equation. Okay, so this is our primary. Now, the nice thing about, although we haven't filled in the values yet, the nice thing about using this for calculus, and this is something you have to memorize, is that you don't need to use the square root. And there are reasons for that. When you actually do the calculus part and do the derivative, and you'd have to do the chain rule and all that, the denominator ends up being a quantity that's always going to be rejected. And so because of that, we're able to kind of use a little bit of a shortcut and write this formula without the square root. Okay, so I'm going to use the distance formula, but I'm going to ignore the square root. So I'm doing the distance between the point 0, 2 and xy. So I would have x minus 0, quantity squared, plus y minus 2, quantity squared. Okay, so that is a formula, though, that has two different variables. So that means I need a secondary equation so that I can eliminate one of the variables. Where am I going to find that secondary equation? If I look back in the problem, was I given another formula? I sure was. Okay, so this right here, y equals x squared plus 1, is my secondary equation. So I'm going to take that and I'm going to plug in the y equals x squared plus 1 in for y into my d formula here. So I'll have d equals, I'm just going to write this as x squared plus, instead of y, I'm going to have x squared plus 1, then your minus 2 all squared. So d equals x squared plus, this will simplify to x squared minus 1 squared. All right, I'm going to go ahead and expand that. So x squared plus, this would be x to the 4th. If I wrote that twice and FOILed, I'd have minus 2x squared and then plus 1. Okay, combine like terms, one last step here. X to the 4th minus x squared plus 1. All right, so I need to go ahead and take the derivative of that function. So it'd be 4x cubed minus 2x. Set that equal to 0, so I should be able to factor out a 2x here, and I'd have 2x squared minus 1. So clearly I get x equals 0, and I get x squared is equal to, let's see, 1/2 when I do that. So I take the square root and I get plus or minus. The square root of 1 is 1, but the square root of 2 is 2. All right, so you can leave it like that. You might recognize this is a pretty well-known one that when you rationalize is root 2 over 2. Okay, at this point I have 3 values that I need to go ahead and test on the sign chart in order to see where, in fact, I will be minimizing my distance. So I have negative root 2 over 2, I have 0, and I have positive radical 2 over 2. And of course this is d prime and d. So as far as kind of understanding what negative root 2 over 2 represents, well, negative root 2 is about negative 1.4 divided by 2. So some of you might remember from trig that's actually approximately negative 0.7. If not, you should be able to at least know that that's not, it's definitely not quite negative 1. So negative 1 is a fair one to test. And then negative 1/2 would be a good one to test here. Positive 1/2 and positive 1. All right, so if I test that back in here, okay, and remember, all I care about is if it's positive or negative. So 2 times negative 1 is obviously negative. 2 times negative 1 squared would be 2, minus 1 would be positive, so that would be a negative value. So decreasing there. All right, negative 1/2. Well, 2 times negative 1/2 is negative, and then 2 times 1, negative 1/2 squared would be 2 times a fourth, which would be 2/4, which would be a half, minus 1 would be also negative. So negative times a negative is a positive, and it would be increasing there then. Okay, 1/2, well, that's going to be the same in the second, in that quantity, 2 times 1/2 squared minus 1. That's going to be negative, but 2 times a half is positive. So we're going to have a negative value here, decreasing. And then the 1, 2 times 1 is positive. 2 times 1 squared would be 2, minus 1 is positive again, so positive here, and increasing. Okay, so I'm going to be decreasing, then increasing, decreasing, then increasing. So you can see here that if I'm looking to minimize my distance, my minimums will occur here at negative root 2 over 2 and again at root 2 over 2. So I would say the x values to minimize the distance would be these values and not this one. Okay, so I'm going to choose positive root 2 over 2 and negative root 2 over 2. Now keep in mind that I was looking at a parabola, and so I have these points, I have my x values. Now I need to go ahead, and this was the point on the y-axis that I was trying to minimize the distance. So now I need to go ahead and find the y values. Well, if you remember, my y equation was y equals x squared plus 1. So it's going to be y equals root 2 over 2 squared plus 1. And really, positive or negative, either one that I plug in, because when I square it, it's going to be positive. This would be 2/4 plus 1, which of course is the same as a half plus 1, which is 3/2. So my 2 points that are going to answer the question that will minimize the distance from 0 to, so my points are negative root 2 over 2, 3/2, and positive root 2 over 2, 3/2. Okay, this last question that we're going to do is very similar to number 3, but this time we have to find a point on the line, 3x plus 4y minus 25 equals 0, which is closest to the origin. Okay, so this time I'm minimizing the distance from a point on that line. Okay, so again, the point on the line would be a point like x, y, and closest to the origin, so 0, 0. So if I'm minimizing my distance, again, I have that distance formula without using, so my 2 points were x, y, and 0, 0. I'm using the distance formula without the radical, so it's just x minus 0 squared, which is x squared, plus y minus 0 squared is y squared. Okay, so that's my distance formula. That's my primary equation. Okay, now I need to have my secondary. Well, my secondary equation is the equation of the line that was given to me. The 3x plus 4y minus 25 equals 0. Now I need to take that equation and either solve for x or y. It doesn't matter. So I'm going to go ahead and solve for x. So I have 3x equals 25 minus 4y. If I just move those, over to the other side, and then divide by 3, I'll have x equals 25 thirds minus 4 thirds y. Okay, so that's pretty ugly, but that's what I have. All right, so I'm going to take that expression for x, and I'm going to plug it back into my primary equation. So I'll have d equals 25 thirds minus 4 thirds y squared plus y squared. All right, now I could write that twice and FOIL it out, but it's just going to get messier and messier with all those fractions. So instead, I'm going to go ahead and take the derivative using the chain rule here. So I'm going to have 2, keep the inside, 25 thirds minus 4 thirds y to the first power times the derivative of the inside would be negative 4 thirds. Plus the derivative of 2y would be, of y squared would be 2y. All right, so I'm going to clean this up. D prime equals, this would be negative 8 thirds times 25 thirds minus 4 thirds y plus 2y. Okay, distribute that through, because remember I have to get this in a way that I can finally set it equal to 0 and solve. So let's see, negative 8 times 25 is negative 200, and then 3 times 3 is ninths, plus negative 8 times negative 4 is 32 over 3 times 3 is 9y, and then plus 2y. All right, so I'm going to go ahead and change that d prime to a 0. And now if I look at this equation, it's a crazy equation, but it's just a linear equation. I want to get rid of all those fractions, so I'm going to multiply both sides by 9, a common denominator of 9. And so, of course, on the left-hand side, I would still have 0. But on the right-hand side, it's going to clean up nicely. Negative 200 plus 32y plus 18y. All right, so I'm going to move the 200 over. So 200 equals, combine like terms, and I would get 50y. Divide both sides by 50, and I get a nice pretty answer of 4 as my y value. Okay, so once I have my y value, I should be able to go ahead and plug back and get my x value. So x is equal to 25 thirds minus 4 thirds times that 4. So x is equal to 25 thirds minus 16 thirds, which is 9 thirds, which is 3. So I end up with a final answer of a point of 3, 4. Okay, and that point represents a point on this line that has the shortest distance to the origin to 0, 0. All right, so thanks for sticking with me. I know that the first two problems were pretty similar to what we did last time, but we maybe were stepping it up a little bit with the difficulty. And then these last two brought in the distance formula. And so I hope that you were able to get all those notes in, and we will definitely be practicing more of this next class. Thanks so much.